We are excited to have everybody here today for our first expert lecture. I'm happy to introduce GoAERO's CEO, Gwen Leiter. Gwen, please take it away.
Thank you, Rebecca. So we are so pleased today to be able to welcome Mike Duffy on our first expert lecture. Rebecca, if you can throw up the slides, that would be great. And so as you all know, GoAERO is a 3-year competition. We are supported by some phenomenal companies and organizations. And those include NASA and Boeing and RTX, as well as a number of different in-kind sponsors. And so too, they also include a variety of organizational partners around the world. Last week we were at AUVSI, Exponential. This coming week we will be at VFS Forum as well. And those are just some of our many partners that we are so privileged to be able to work among. Today we have our very first master lecture, our expert lecture by Michael Duffy. Mike is Vice President of Product at Electric Power Systems. In this role, he leads a team that brings high power battery systems to aerospace products by electrifying flight and reducing carbon emissions for transportation. Prior to EP Systems, he worked at Boeing for 18 years in Boeing Vertical Lift, Boeing Research and Technology, and Space and Launch. He holds 16 patents in vertical lift technology and unmanned systems technology. And his favorite activities include triathlons, hiking, and backyard fires. And several years ago, he also raised a whole troop of chickens, as I remember correctly. So without further ado, it gives me great pleasure to welcome Mike Duffy as our first expert lecture for the GoAERO Prize. Thanks, Mike.
Thanks, Gwen. Okay, let me share my screen and
just for everybody, we will be taking questions at the end. You can ask questions in the QA. We will be unable to take them in real time due to the number of attendees today. But I will make sure that we get to as many as possible at the end. Thank you so much.
Okay, let me share my screen and let me know if you guys can see that.
Yes, we
can.
Thank you so much. Well, thank you all for coming, and I appreciate you guys spending the time to listen to me, and I hope I have some information for you guys that is very helpful for your efforts. And like Gwen said, I've been in the industry for quite a while. Just a quick introduction of myself. My name is Michael Duffy. I'm the Vice President of Product. Like Gwen said, I worked at Boeing for quite a while, and I worked on quite a few different projects. I started as an aerospace engineer in aerodynamics, and my first project was with the V-22 Osprey, which was a tilt rotor. And I did various rotor designs and other wind tunnel testing and flight testing on that aircraft, and became a rotorcraft sort of expert in that domain. And then 10 years into my career, I started working on a cargo air vehicle, which was an electric drone that Boeing was working to carry products to and from warehouses. We also did a project with Disney World where we actually took that same aircraft, put an outer shell on it. It looked like an X-wing. We flew it over Disney World for a few shows. That's actually where I met the founder of Electric Power Systems. And he asked me to come over and lead the product group 3 years ago, and that's what I've been doing ever since. Electric Power Systems is the leader, I would say, in aviation power. We've delivered quite a lot of modules to electric aircraft companies, from fixed wing aircraft to eVTOLs, to even underwater vehicles in space. So that's kind of my expertise. But today I want to talk to you about two things. One, since I'm the first lecturer, which I'm honored to be, I want to talk a little bit about the mission that you guys are about to embark on, and how it's important. So essentially, the mission itself is to basically do rescue and also bring goods to where you need it, and it's very difficult to get there. And I think this is a really cool concept, and I'm a big fan of this idea. And so I'm hoping that you guys are successful in your designs. I think this is going to have a big impact on the world, so I'm actually really excited to be part of it. And the way I like the way how GoAERO is doing this. It's basically a 3-mission aircraft or system, and you basically it's the usefulness of your aircraft that's going to matter. So you're going to have to size your aircraft to do a long payload mission, but also be able to maneuver and also be able to do it in adverse conditions, which is what a real world aircraft would have to do. And in the many years I worked at Boeing, it's those other pieces, not just the size of it, but also how productive is it? Can it operate in winds? Can it operate in maneuvering? And so it's going to be a very interesting challenge for you guys to do this. So I was hoping to start off this first lecture with just some really basic physics stuff, and then I'll talk about, well, batteries. And I'm hoping it'll be very interesting as we go forward. So let me get started. So let me talk about the power of flight, and I'm not talking how cool flight is, but also this is like one of my favorite charts. It's kind of old, but essentially it shows two really important parameters for how you move stuff around. You have to figure out how fast you want to move something, and then you also have to figure out how much energy it's going to take to move it. And this plot essentially shows you that the most efficient way to move things is by sea. So you can see that the lowest energy required is the sea, but you also notice that's the slowest way to move things. If you go to the upper right corner here, you can see that the fastest way to move things is air. And you have two different types of moving things. You can move it with a fixed wing aircraft, or you can move it with a helicopter. And those two things have different speeds, but you can see that the energy is very high. And I think this is the purpose of this lecture, is to say, you really need to optimize your energy. You have a very limited constraint of energy, and therefore you're going to have to find a way to make your system as efficient as possible, either through weight, or through aerodynamics, or through mission or ConOps. But the benefit of this is that you get to be able to do something that you can't do with a ship or a car, and you can basically get places that no one else can get to. And I think that's what makes it really cool. And so that's what makes this prize special. So this is a quick lecture on momentum theory. And I want you to just think about, a lot of people focus on the rotor blades or the disc, the actual rotors themselves. I want you to just take that out of your mind and throw it away. I want you to think of your aircraft as a lifting body, and essentially the swept area that your rotor sweeps through is a disc, and that disc is like your wing. Okay, don't worry about how many blades you have or twist or anything like that. It's really about how much disc air you have. That's the first order principle of power and thrust. And essentially, the bigger the rotor disc you have, the more air you can move with less energy. Okay, so this is a really cool plot because it shows you what the air is doing as it goes through your disc. It's actually pushing the air through the disc and going out through the bottom. And you're basically taking the weight of the air and you're translating that into the weight of the aircraft. So you have to push a lot of air, because it's not very dense, through your rotor to lift a lot of weight. Okay, so it's the basic momentum theory. But why that's important is that when you're choosing your configuration or you're choosing how you're going to do this mission, you want to keep in mind that the disc area, the amount of swept area that all your discs combine equal, is going to define how much power you're going to need. And high power means you're going to need a lot of energy. So it's very efficient to have a very large disc. So in this plot, helicopters are very efficient in hover, and tilt rotors, tilt wings, lifting fans, all those smaller disc aircraft are not as efficient in hover. They take a lot more power. And I'd like to do a really quick example. If you take the exact same helicopter, weighs 1,000 pounds in all three examples, and you put three different size rotors, a 2-foot rotor, a 5-foot rotor, and a 10-foot rotor, and you basically calculate the horsepower you need to lift off the ground, it's significantly higher for the smaller disc. 625 horsepower for a 2-foot rotor, 333 horsepower for a 5-foot rotor, and 160 horsepower for a 10-foot rotor. So this is something to keep in mind when you're sizing your aircraft. You want to make sure you have enough disc area for hover so that it doesn't take a lot of energy and you don't need a very large power plant. But you pay a price. If you are very efficient in hover, which means you have a very big disc, you also are very inefficient in cruise. So you have to actually find a balance between hover and cruise. When you're cruising, you have a very large rotor. It means you have a lot of drag, and that means you have a lot of power required just to go from A to B. So you have to optimize your system for your mission. And so the way to do that, there's a lot of really cool papers out there to do that, but I'm going to recommend a paper that a colleague of mine wrote in Cornell. It basically takes the different configurations. So you have helicopter, multi-rotor, lift fan, tilt rotor, tilt wings, all have different benefits. Some are good in cruise, some are good in hover, some are really simple, some have complex parts, they have more weight, and basically does a very simple, I would say, uses just a couple simple calculations for weight, for power, for drag, and optimizes it for different mission sizes. So if you have a very fast, you have a very high speed mission, you want to do it very quickly, you're probably going to want to go towards a tilt rotor or tilt wing. If you have a very slow mission, okay, you might want to do a multi-rotor or helicopter. If you have long range, you probably want to do something more efficient in cruise. If you have a short range, you probably want to do something more efficient in hover. So these charts will be available online, but essentially this is a link to a paper that he wrote. Akshay, he wrote this paper, and it's got a lot of really good equations in it. You can basically take them right out of there, put them in an Excel spreadsheet, and you can do these calculations and optimize for your mission. And the reason I'm showing you all this is because the key to all this is you're going to have to size your aircraft to your power plant, and you're going to eventually need some kind of power system to lift off the ground. So one last thing I want to show you in the math realm, then I'll start talking about batteries, is the range equation, the Breguet range equation. And this Breguet range equation has been modified specifically for electric aircraft. And it's a very simple equation, but it basically allows you to take your battery mass fraction, the efficiency that you are in cruise, your propulsive efficiency, and your battery efficiency, put them all together and calculate how far you can go. And this is a really simple back of the envelope calculation to determine how much energy you're going to need on board and how efficient that energy has to be in order to do your mission. It's a good back of the envelope battery check. See if your battery is big enough for what you need to do. And again, depending on the configuration, if you have a lift rotor, like a helicopter, you're going to have a very inefficient cruise, but you have a very efficient hover. And on the far right, you have a very efficient wing-borne aircraft, like a winged aircraft, but you have very high hover power. And no matter what kind of aircraft you have, you want to be very efficient with your batteries. And you'll see that when I made this presentation years ago, the state-of-the-art batteries that you could install were about 160 to 200 watt-hours per kilogram. And that's essentially one of the metrics we use to look at how much energy you can store in a certain weight. Watt-hours is basically like kilowatt-hours, and kilograms is your weight. And the more efficient you are at this watt-hours per kilogram, the less weight it costs for a given energy. Today, we're looking at installed weights of 260 watt-hours per kilogram, which is pretty good. So let's talk about batteries. This might be obvious, it might not be obvious, but there's a lot of different ways to store energy. And this plot is really cool because it kind of shows you the trade-off you have between energy per weight and power per weight. So on the y-axis is power, and on the x-axis is energy. And there's various different things within this realm, but if you look at the battery areas, You can see that lead acid, nickel cadmium, all those older technologies are on the left, and they're not very high energy and they're not very high power. And then if you look to the right, you see traditional fuels like gasoline, methanol, hydrogen, all those great things. And in the middle, you see some more state-of-the-art batteries, where there's different kinds of chemistries, lithium ion, zinc, silicon are some of the newer technologies. This plot is from 2005, so it didn't exist then. But I highlight the aviation space, and essentially we're trying to get batteries to move into that gasoline realm where it can do the same power and have the same energy. And you can see there's a long way to go. We're not there yet. So I put some numbers in here because I wanted to show, let me just get rid of something on my screen that I can't read all my slides here. I wanted to show 4 challenges that I think batteries have to become aviation products. 1, safety and certification. You've got lots of different Part 23s. There's different regulators, FAA, EASA, JCAB, etc. Takes 2 to 10 years, depending on what you're trying to certify. It costs millions of dollars. Very expensive process, but it's there to keep everyone safe. Cost is something I'll talk about a lot in this presentation because it's one of the big factors. But one thing to keep in mind is that batteries for aerospace are going to cost more than batteries for automotive because they require more energy, they require more power, more cycles. It's a lot of things. You're paying for the high technology, and automotive is actually trying to race to the bottom. Okay, they don't need any more energy. They have enough energy now. They want to make them cheap. So that's one thing to keep in mind. Weight is going to be your #1 driver, probably for your sizing. And it's going to be based on how much power, what discharge rate, what energy you need, the cycle life, charge rates, can you cool them, et cetera, et cetera. And it's going to be a big part of your size because it's going to be 20 to 40% of the vehicle weight. And then, of course, finally, you've got infrastructure. You have to find a way to actually charge these things. And if you look at today's chargers, Tesla, for example, has a supercharger. The highest it can charge is 250 kilowatts. In aviation, when you want to go high speed, quick turnaround, you're going to need somewhere between 250 minimum to 1,000 kilowatts. So big challenges that we have to overcome. And I'll say the first one is the perception of lithium-ion batteries. Obviously, lithium-ion batteries are amazing technology. They're used today in automotive. You also see lots of press around fires. And one thing about automotive that's interesting is that they don't currently have a requirement, or it's only recently changing to be contained. Meaning, if you have an electric battery fire on your Tesla or whatever electric car you have, it's allowed to burn the car down. And the reason is because you can get out of the car at any time. You can stop the car and get out. This is not the case in aviation. If you have a battery fire and you're in the air, it means you have to basically contain that energy. You can't have it burn the aircraft down while you're flying. So how do you do that? And there's a lot of ways to do that. There's different regulatory approaches. There's different solutions out there, but there's a spectrum, I would say, from left to right. And you can basically start all the way at the left, which is the cells just don't go into thermal runaway. And for that, you basically have very stable chemistries. But for the high technology, high energy release batteries, you don't have that opportunity. They just don't do that. They actually have, they're very combustible in some ways. They have their own combustible system within themselves. They don't need any oxygen to burn. So one way to approach that is to do cell-to-cell propagation mitigation. And all that means is if you have a packaging system that has many, many cells, and one of those cells goes into thermal runaway, you basically stop it from propagating to the next cell. Now, this is a really good idea. However, the challenge with cell-to-cell propagation is it requires very large packaging overheads. You have to space the cells out. You have to ensure that it doesn't go from one cell to the next. You have to make sure there's no shorting between them. And this winds up costing the packaging weight very high, to the tune of, it could be as high as 200% or 20 times the weight of the batteries just to have all that packaging in there. So It's really, really hard to do cell-to-cell propagation and still have a lightweight package. You can do module level mitigation, which is you basically contain the energy within a certain box size and you allow it to propagate within that box size, but then you contain it within that box. It does not go to another box. And that's essentially a module. You also have battery level, which essentially means that you can have an entire system go up, but it's contained within that battery system. And then you have vehicle level, which is what automotive basically does, except for you have the passengers just jump out of the car. You can't have them do that in an aircraft. So we like module and battery system level. We think that's the right approach. And in fact, today there is a standard, the FAA, that's called DO311. And that standard is used to certify lithium batteries on the 787 and the A350. And essentially it mandates that you must have all the cells in your battery go up into thermal runaway, and they must be contained within that space so that all the passengers can get out safely when it lands. And you allow that air or gas to go overboard because there's so much energy, it has to go somewhere. It can't just stay inside the box. So there's a little vent that goes overboard. And that's essentially what we are certifying to at Electric Power Systems, the DO311A. And we think that is the most sensible path in terms of safety, but also the most sensible path in terms of actually getting regulators to agree on what's the safest way to go. And we're going through that process right now. And just to give you a sense of why we like the module level packaging, this is a thermal imaging camera of one of our modules. It is in thermal runaway on the left and on the right. You will notice that you cannot see any smoke or fire, and every cell within that module is in thermal runaway, and all the gases are being overboarded off the aircraft. In this case, it's in a Connex container to show the safety of it, but essentially you can see there's no smoke or gas. So if this was to happen on an aircraft, it'd be completely contained within that module. Another key thing about this image is that it's showing the packaging that we're using is a special packaging. It's very high energy containment capable, and it's only 17% of the weight of the battery. So that means the majority of the weight on this pack is all cells, about 80% or more. So let's talk about, that's thermal runaway. That's one of our challenges. Another challenge is cost. So why is it more expensive for aerospace batteries than automotive batteries? Well, let's just talk about scale. If you look at a number of gigawatt hours that automotive batteries are being produced at, and this is an older chart because it goes to 2017, but essentially you can see that the level of gigawatt hours being produced for automotive is tens of thousands of times greater. In fact, today for electric aircraft batteries, it's less than a gigawatt hour, which means that the cost is going to be a little higher, but also because you have higher standards, right? You have to contain all the energy. So you'll see that the cost for aerospace batteries will come down, but I don't think they'll ever be at full parity with automotive. Let's talk about another thing with cost. If you have an iPhone, you know this happens. It basically is a simple thing. Batteries don't last forever. They have a life, and they will run out of energy and storage capacity over time. And this simply talks about what's the difference between electric aircraft and cars. So if you look at a battery, you have two different terms. You can say, what's my state of charge, which is the top row. If you have 100% state of charge, that means you're fully charged. And if you have 0, that means you're fully emptied. There's also another way of saying the same thing, which is depth of discharge. And when we talk about cycle life, depth of discharge is sort of what we use. So when you hear someone say there's 0% depth of discharge, it's a full battery. And if you have 100% depth of discharge, you've taken all the energy out. Why this matters is because cycle life is very, very dependent on this depth of discharge. So for example, a typical aircraft mission, because it's so energy constrained, requires that you use up almost the entire battery every single time you fly. You use almost 80% up of your depth of discharge, and you have 20% remaining for some reserve. For a car, typical mission is much, much less depth of discharge. You only use a top end of your battery, and that means that those car batteries are going to last a very long time. And just to give you a quick example of that, I have a little notional plot. This is how many cycles you can get with various depths of discharge. So if you're like a car, this blue line, you only use 30% of your battery, the top end, you're going to get a lot more cycles. If you use half your battery, you're going to get even less. And if you deplete your battery every single time you fly all the way to zero, you're going to get even less cycles because it's basically damaging the battery over time. So keep in mind when you're sizing your system, how many cycles you're going to need and what's the depth of discharge, how much battery you're going to use. You can't use the whole amount every time. So let me just talk lastly, this is my last section, it's about aviation batteries specifically. I know I've been talking a lot about that, but I do want to do a little discussion around some of the specifics around aviation batteries. So one thing you have to do with aviation batteries, you absolutely have to minimize weight. Now, you still have to build a box to carry everything, but you have to have a way to cool them sometimes if you're going to recharge them quickly. You have to have a place where you can put the gas if it is a thermal runaway. You have to have a way to communicate to all the modules in your battery, and you also have to be able to connect them all to get high voltage. So at EP Systems, we basically develop all of these pieces. Essentially, we have modules, which are those individual building blocks, and we size those to whatever size aircraft and voltage. Then you also have a battery management system. And this is important for lithium batteries because you have to be able to maintain a certain voltage minimum and a certain voltage maximum. Also, you have to maintain a certain temperature range. And that's very important. So that's what a battery management system would do. It allows the system to be turned on and off as you need to. And then you also have things like cooling, and you also have things like communication. And then, of course, you have to be able to charge the batteries. So essentially, these are all the elements and pieces for an aviation battery that you need when you're building a certified battery for flight. So our system essentially has and is being flown on quite a few aircraft, fixed wing aircraft, sea gliders, eVTOLs have been flying with our system. We've flown, various different brands of companies, and we're currently sort of going through this process with a couple companies to go through FAA certification and as well as EASA certification. So let's talk about technology and where we're going with batteries. So in general, we look at various chemistries as we get to better and better energy. So the current products that we see on the market today are mostly lithium cobalt or lithium NMC. And that essentially is where we're at today in terms of energy density is about 280 watt hours per kilogram at the cell. When you package those into in a module, you're going to lose some of that energy. And that's essentially what the numbers on the right there are saying. When you start putting them into a battery, you'll start seeing their weight go up. And these are the numbers we typically quote. And these are the numbers you need to use when you size your system, because you're not going to get just the cell weight. You're going to get the cell plus all the stuff that you have to build around it. You also notice that there's two different types of products typically out there. There's an energy product and there's a power product. Energy products are good for lower power discharges, like a fixed wing aircraft. There's no hover required. Takeoff isn't as demanding as a hover mission. And then you have a power product, and you'll notice that the energy is less. The reason it's less is because you have to give up some energy to allow for more power. And so, for example, when you're building your system, you might not be able to get the peak energy density that you see out there because you're going to have to get a cell that actually has high powered discharge. And it goes back to that plot that I was showing earlier that had energy and power, and essentially there's a Pareto front of where you can go. The next technology we're seeing in terms of batteries is silicon anode. This is a much higher density energy system, but there are some things about silicon that's interesting in terms of the breathability of the cell. The cell doesn't just sit there statically when you charge and discharge. It'll actually will breathe. It'll actually get a little thicker and get a little thinner. And so that's another packaging constraint that you have to work with when you get these higher technologies. And then in the future, we're looking at solid states electrolytes like lithium metal, And this is a technology that will allow for really, really high energy densities, but there are a lot of technical issues in terms of cycle life that you have to work with. And so as you see the technology gets better, you'll see the energy density is getting better. But of course, as you get to higher energy densities, you have more packaging constraints. So you're kind of always working around these new issues as you go into this technology. So just a quick plug on EP Systems. We're based in Logan, Utah. We're a startup. We've been around since 2016, and we have about 130 employees. Quite a few aircraft have been flying with us. About 12 aircraft have flown with our batteries that we know to date. Hundreds of hours of flights, and we're currently about to submit our first certification, which is called a TSO, with the FAA. So we're really excited to do that, and we're hoping to see some of our aircraft certified really soon. I think one of the first ones we're going to see certified will be Diamond, which makes a trainer aircraft. We are shipping quite a few modules, and of course, always interested in picking up folks who need those. And then, last year we flew our first flight with Diamond, which is an electric trainer aircraft. We think there's a pretty cool opportunity to reduce the cost of flight training. And we're also going through our TSO, which this is just a quick picture of some of the testing we're doing. And that's about it. That's all I know right now about batteries. But if you have any questions, I'm here to answer some questions.
Michael, thank you so much for your time. We do have some questions. I want to remind everyone that you can find the QA at the bottom of your screen. You can type your questions there. To answer a question that I saw in the chat just quickly, we will have this lecture in its entirety available on the HeroX platform. It's herox.com/GoAERO. Additionally, Michael, we have a question for you that is, what GoAERO rules do you believe impact the selection of energy power, and how do they impact it?
Yeah, so I looked at the rules, and my understanding is that you have a timeline, a time frame that you have to deliver a certain amount of payload at a minimum, and then you get additional points for either shorter time or more payload. And so essentially what you'll want to do is you'll want to size it to the minimum at least, and then you'll want to see how far you can go with that in terms of still meeting the constraints of maneuverability. And as you build a bigger aircraft, you're going to need more power. You're also going to need to be able to fit it in a certain space. I know there's some space constraints and maneuverability. So you have to look at footprint versus how big you want to be.
Thank you. We have lots of questions coming in here. Thank you. I have, how accurate is the Briguet range equation for VTOL configurations?
Well, it's only as accurate as the numbers you put in. So it is physics. I mean, if you put the correct L/D, the correct weight fractions, everything, it will be 100% accurate. But getting your L/D correct in every condition, getting your battery mass fraction correct, getting your energy density correct, and your efficiencies correct are all part of the challenge. And in some of the papers that I had recommended in this talk, there are equations you can use for weight, and there's equations you can use for efficiency, for your prop, and other things that will help you size your system, give you a general starting point. And then as you refine your system, you get more data from flight test or wind tunnel testing or however you collect it, you'll get more and more accurate.
Given the much higher specific energy of gasoline and hydrogen fuel cells, why do you think someone would want to go for a 100% battery powered vehicle for this competition? And, note here that, just for everybody, that a battery powered vehicle is not required for the GoAERO competition. But this is the question.
Absolutely. It is a really good question. And in fact, there is no guarantee that a battery is better for this mission in any way. you have to do the analysis. The reason that electric is nice is because you're allowed to distribute, you can distribute your rotors in various places on the aircraft that might be beneficial. If you just want to build a helicopter to do the mission, then you might be able to do that. In that case, it's just a single rotor. But if you start to put in, if you want to be able to go long range, or you want to be able to be very efficient in cruise, helicopters aren't as efficient as a winged aircraft. And so a lot of eVTOLs companies are looking at that paradigm right now.
Um, how does the increased weight of active liquid cooling affect the decision to utilize cooling during discharge versus just during ground-based charging? And what are the cycle implications on the battery life?
Great question. So cooling, typically for our customers at least, there's enough battery mass that the thermal energy is completely contained within the battery, and you don't really need to cool in flight unless you have a hybrid system, which is usually a combination of a gas powered system and a battery. And that in that case, your battery is smaller. And because it's smaller, it needs to put out a lot more power. And so in those cases, people tend to want to use liquid cooling. So I would say from a sizing perspective, if you're all electric, you probably won't need to cool in flight. Now, when you're on the ground, you will find that between your missions, if you want to be able to fly often, and especially if in your mission you're flying for GoAERO, if you're doing lots of sorties and you're charging or swapping batteries, if you're swapping batteries, you won't need to cool. But if you're keeping the same batteries and you're trying to charge them, you'll definitely need to cool because the batteries will get hot over time. And as you land, you'll land at a high temperature, and in order to turn the aircraft around, you'll have to charge it. And when the batteries are on the ground, they don't cool quickly unless you have some kind of medium circulating through them to cool them off. Because again, there's such a huge thermal mass that they require some liquid cooling. So most of our customers only cool the battery on the ground for all electric. And then for hybrid, it tends to be cooling in the air as needed. And then to your point of cycle life, this is a very interesting question. It's a complex question because batteries don't like to be charged hot, but they do like to be discharged hot. So you'll get a little but in general, cycle life is you want to keep it at a pretty nominal temperature. 25 degrees C is the best for cycle life. If you're storing a battery, it wants to be very cold. You want to keep them very cold if you're storing them, but if you're just using them for flight, you want to keep them at a pretty nominal temperature, 25 degrees Celsius.
Thank you. What energy system risks should participants track as they settle on an approach and work to implement?
Risks, good question. So you'll want to understand your power profile very well. Some of the risks I've seen come to fruition is that the batteries get hotter than they expected, and then that limits your mission. In fact, I've seen it many times where you size for energy, but you don't size for power correctly, and then you wind up actually not using all the energy. So one of the major risks is thermal management of your battery. If your aircraft winds up taking more power than you thought, or it's not cooling like you thought it was going to cool, you'll wind up having to land sooner than you want to, and you won't use all that energy. So I would say one of the major risks is thermal.
Uh, Typically, what separation distance is needed between battery packs to protect other batteries from the one undergoing a thermal runaway?
That's a great question. It'll depend on the system, but our system is a 1/4 inch. We've sized it such that you can put them within a 1/4 inch of each other. And if you have a thermal runaway event, it will not heat up the other module if you're at least a 1/4 inch away. It also depends on sort of how you're mounting them. If you're mounting them in a very thermally conductive path, you have to make sure you keep in mind how thermally conductive that is. But again, our modules have an isolation system that allows you to mount them within a 1/4 inch in any direction. And there should be no concern about propagation between those modules if there's a thermal event.
What are the options you believe are available to GoAERO participants in the available timeframe and with likely budget?
Yeah, so that's a great question. Obviously, there's a lot of hobby batteries available, and that might be good for your prototype aircraft. As you start to get into a more serious sort of, situation with trying to certify, then you'll want to look at a more aerospace level battery. And in fact, we are looking at taking used batteries from our customers and having them available for sale, so gently used, if you will. And so those might be available for things like this, where it'd be significantly reduced cost because they're not brand new, they've been used. But for missions like what you guys are doing, it probably would be fine. So you could look at like maybe the aftermarket, if you will, or used batteries, which we'd have available. You can look at obviously those hobby batteries, which generally come from China, I would say. And then there are a few other companies out there doing aviation batteries. So what I've seen is a lot of companies wind up building their own batteries, maybe at their own peril. But yeah, I think that there are batteries available now. Like, I mean, you can buy these batteries off the shelf today. Obviously, hobby batteries are available today. It's just a matter of kind of making sure they meet your requirements.
What's out there for hybrid gas/electric systems?
So the hybrid one is a good question. For an eVTOL, for example, if we're talking about vertical lift, there's really only one, I mean, probably only one hybrid configuration you can do, and that is it's called series hybrid. And what that means is you have a battery pack, and you have a gas engine, and then you have a bus that's between them, and that gas engine will turn a generator. That generator will generate power, and it'll put the energy on the bus. If you want to store energy, it'll go to the battery, and if you want to use energy, the battery will pick it up. And it sounds like that'd be a parallel, but they call it series. And those two energy sources can be sized at different levels. You could have like 50% energy come from your battery and 50% come from your gas energy. You could do 90-20, 90-10. There's the whole like gambit of how you want to size it. The good thing about it is you get a fuel tank and you get a high energy density. The bad thing about it is there's a ton of weight that you have to add, because you're adding a generator that's generating power that you wouldn't need if you had only battery. So hybrid is more of a complex sizing situation. And what's out there today? Well, they're pretty expensive. I'm not an expert in hybrid, I'll be honest, but I know there's companies like Saffron and others that have kind of generators available. Diamond actually has a generator and Ostro engine combination. I would just search the internet. I'm not an expert in hybrid.
What available resources can you recommend to participants? Any good hidden ones that aren't so well known?
I guess it depends on what you mean by resources, but I think sizing wise, I gave you a pretty good starting point there. In terms of batteries, trying to think if you can go to a lot of the hobby websites. I don't have any specific secret place that you can find great resources I can think of off the top of my head.
Uh, does EPS offer off-the-shelf batteries sizes, or are all batteries made to order custom?
That's a great question. Yep, that I can answer. They are off the shelf, and we size the system to your needs, but there's a building block, a module that essentially is the same for everybody, and then we just size the number of modules for your aircraft. So I would call it modified off the shelf, if you will, depending on your needs.
What were the midpoint boxes in the battery layout chart?
That's a good question. So it is a fuse, and it is also a disconnect. So when you push the modules together, you're building up higher and higher voltage every time you push them together in series. And this midpoint box essentially allows you to break that voltage, and that way it makes it safer to handle. And then when you put all your modules together and you have everything connected, there's still no path for the energy to go through. You put the fuse in, and that fuse actually then activates the string. And then there's also a disconnect inside the midpoint, in the battery management unit, which actually has a contactor. So there's actually two places you can break voltage: at the midpoint, which is somewhere in the middle of the string, and then also at the battery management unit.
What is your prognosis about metal air battery technology, LiAir, etc.?
Um, that's a good question. So I'm not a chemistry expert, but essentially there is some kind of byproduct with the lithium air in which you're using the air itself as like a cathode. And so it's definitely out there. I haven't seen any. We test cells. We probably test a new cell every month, and because we're always trying to find the best chemistry to put in our batteries and go to that next product. And I have not seen anyone propose lithium air cell to us. One of our major hurdles for our cell providers is, can you provide me a sample for that cell? If they can't provide us a sample cell, then we know it doesn't exist.
What types of batteries are the most weight efficient? This person was looking into pouch cells and wants to know what you think of those cells.
Great idea. Great question. I mean, so the the product we deliver right now, Epic, is actually a pouch cell. We like pouch cells for a couple reasons. One, they are very weight efficient in terms of packaging. You can stick them all together in a box, whereas cylindrical cells, you have to space them out, and they have, a lot of air between them. So we like the pouch cells. They're also nice for getting thermal management. So you can basically put cooling plates right against the walls, and between them pulls the heat out pretty quickly. And then we also like them because of how rapidly you can get new cell technology. So typically it takes a little longer for the process of a new cell chemistry to get put into a can format. and and sometimes you lose some of the energy density when you do that. So we like the pouch cells over cylindrical. But then there's also the downside of pouch cells is that you can't really do cell-to-cell propagation mitigation. So if you want to be able to stop propagation between them, you have to put a lot of material between them. Whereas with cylindrical cells, there's kind of a natural cell-to-cell propagation mitigation approach.
What is the EPS unit module power output?
So Epic One, one of the modules is 2.3 kilowatt hours, and it puts out 5C continuous. So 5C essentially is 5 times 2.3 kilowatt hours. So, what would that be? 10 kilowatts or something in that range. And then 2.0, the new version of our module that we're releasing, is 3.1 kilowatt hours, and that's a little less, maybe 2 or 3C continuous. So maybe again 10 or 15 kilowatts per module.
Uh, can a regenerative or cogeneration approach to maintaining energy be tried, or is battery for or is battery use defined for GoAERO regulation? I do not believe, I think I can answer this one. We do not require any specific power source for GoAERO's competition. Does the EPS power management system permit power input from an engine generator and manage that?
Yes. A battery is an awesome way to store energy. And so you can get energy from the grid. You can plug it into the ground, or you can generate energy from a generator on board and store it on the battery. It's a really nice way to keep energy maintained. And what some folks do with our batteries is they use our batteries only for peaks. So they have a gas powered engine and then they use the battery to give it a boost or to absorb energy from the prop to slow down, or to store energy while it's in cruise, because you have a big enough engine to fly the aircraft and produce energy. So yes.
What is the EPS unit module weight?
1.0 is 11.5 kilograms or 2.3 kilowatt hours, and 2.0 is it's on our website, but it's 3.1 kilowatt hours at 11.5 as well, more or less, kilograms. So significantly more energy in 2.0.
What is the weight fraction per power system size needed to account for your power management system?
Good question. It's going to depend on how big your system is, but the battery power management unit is about, depending on what you put in there, 6 to 8 kilograms. So for each string of batteries, you have one of those 6 to 8 kilograms.
All right. Well, thank you so much, Michael. We really appreciate your time today. And thank you to everyone who attended our first GoAERO expert lecture. We will have this expert lecture available for you to view on our website and on the HeroX platform, herox.com/GoAERO. And we hope that you continue to follow us and sign up for our newsletter. So we hope to see you all soon.
Thank you, Rebecca. Thank you, everyone, for listening.
Have a great day.
Thank you, Michael.